Hello, everyone. Welcome to the second student sensory rig seminar series. My name is Zhang Li. I will be the chair of today's talk, and I'm also one of the members in the student-led research interest group. The primary aim of our sensory rig group is to share research in the area of sensor and sensing technology. We hope the student seminar series will enable knowledge share and foster collaborations. Please visit our website to explore more about our organization. If you would like to present your research or interested in joining our group, please do not hesitate to email us. The title of today's talk is Chemical Exposure to Disinfection Byproduct Interacting on Personal Face Masks. We're very excited to have Daniel Blomdahl here. Daniel is a MS PhD student in the Environmental and Water Resources Engineering and Building Energy and Environment programs. He completed his bachelor's degree in engineering physics from Whitworth University in 2019. Daniel is a member of Dr. Powell Mistel's research group. He uses a state-of-the-art analytical instrument to measure concentrations of volatile and semi-volatile organic compounds and their impact on human health and climate. Daniel is particularly interested in urban air quality and in characterizing exposure to indoor air pollutants. Before the talk begins, I would like to remind you that you can ask questions at any time by using the chat box. We'll collect the questions and ask the presenter at the end of the talk. Now I would like to hand over to Daniel, and the time is yours.
Thank you so much for the introduction, Song Lee, and I'll share my screen really quickly. So as he mentioned, my name is Daniel Blomdahl. I'd like to welcome everyone on Zoom and those watching on YouTube. And today I'll be presenting on exposure to indoor air pollutants during hydrogen peroxide and bleach disinfection events. So first, I'll give some acknowledgements about my research team. I'll give some motivation for why this research is important, and then look at some past findings. Then I'll look at how the experiment was set up and some initial results. So first, our research team is made up mainly of the civil engineering department and the chemical engineering department here at UT. There are also a few other institutions represented mainly in advisory roles. And then I'd like to thank the National Science Foundation for their financial support, as well as the Dr. Tanya Hunter Research Group for inviting me to this talk today. So due to the pandemic, there's been an increase in the number of disinfection events, especially in indoor spaces. That's mainly to prevent the spread of the COVID-19 by disinfecting surfaces. And so I'll give a few examples. The first example is in schools. And so there's these fogger machines, as you can see pictured in the three pictures here. And they basically use some kind of disinfectant spray and then kind of make a bunch of small droplets that fall onto surfaces and then disinfect the surfaces. So you can see here that there's in school districts, they're using these fogger machines, as well as these public transit systems. Valley Metro is Phoenix, Arizona's public transit system. So it's a pretty popular one. And so there's a lot of people that ride these public transit trains and rail vehicles. Another example is in movie theaters. And so you see some tweets here from a few prominent theater companies advertising how they sanitize their theaters before each movie. And then finally, a few pictures. This is just taken a few days ago. This is the White House press briefing room. And you can see there's these fogger machines that spray disinfectant all around the room and fill the air with the disinfectant. So the reason that these disinfection events might be problematic is that so many droplets that are sprayed evaporate, and especially VOCs, which are volatile organic compounds, they want to be in the gas phase instead of the droplet and liquid phase. So they evaporate and then are distributed throughout the indoor space. A concept that I will familiar you all with is called the air exchange rate. And that is a trait of kind of any indoor space. And it's defined as the flow rate over the volume. And it's in units of basically the amount of volume per hour. So a very large air exchange rate is a space that's flushed out and very well ventilated, while a very low air exchange rate is one that's the air is very stagnant, and anything that's emitted into the room, the concentrations from that will stay elevated for a long time. For this experiments, we used hydrogen peroxide and bleach because they're very popular and they're widely available. And so that's what a lot of the indoor spaces would be disinfected with. So it'd be most applicable and relevant. So looking at some past findings, so the home campaign, you can see the graph here from that. That was done a few years ago in 2018 at the UT Test House, which is a full-scale house located at the J.J. Pickle Research Campus, a few miles north of the main campus at UT. And they did a few bleach cleaning events and found spikes in nitrogen-containing compounds like monochloramine and dichloramine, which contain the chlorine from the sodium hypochlorite bleach ingredient. And there's been a few other experiments and campaigns that have looked at these bleach cleaning events, but there's been much less looked at the hydrogen peroxide byproducts from disinfection events. So I'll be discussing that a bit more in depth today. So our research project aims were kind of split into two phases. The first phase was to finding the concentrations of these volatile compounds in indoor spaces after a disinfection event, in both hydrogen peroxide and bleach. And then the second phase is looking at personal face masks and how wearing a surgical face mask or a cotton face mask might reduce the exposure that someone would be exposed to from these VOCs. And you notice that the first aim is bolded, and that's because we finished that stage. We're kind of midway through the experiment now, but I'll be able to give some pilot study results from the second stage regarding face masks. So the experiment conditions, we used a environmental chamber, a stainless steel chamber up at the Pickle Research Campus, and we had a relatively high air exchange rate for an indoor space. We basically put 6 tables inside and then sprayed those tables with 300 milliliters of the disinfection solution, both consumer grade and scientific grade bleach and hydrogen peroxide. Consumer grade for both the bleach and hydrogen peroxide is expected to be much less pure than scientific grade. So there'll be a bit more additives. The quality control for a few ingredients won't be as strict. And so we expect to see a lot more wide range of VOCs found in the consumer grade versus scientific grade. And for the sake of realistic conditions, we will be using the consumer grade disinfection ingredients for the second stage, because that's what people will be using in their homes and indoor spaces. Looking at the instrumentation, so we used 2 main devices. The first was a Vocus mass spectrometer, what's known as a proton transfer reaction time of flight mass spectrometer. And the way that instrument works is that there's these ions that are made that attach through a chemical reaction to the VOC that we're looking at, the compound. And then the device measures the time of flight with which the compound goes through a space, and then you can measure the chemical mass very precisely with those. And the Vocus is kind of the world leader in this kind of technology. It can measure in real time with more than one measurement per second, and can measure below 1 part per trillion, so for every trillion molecules, they can measure 1 compound. So very, very trace levels of gas. Another thing is that it has very good mass resolution. So you can see here the yellow and the blue are previous iterations of this instrument, but ours can elucidate many, many different peaks and many different formulas. So it's well versed for this kind of experiment where we're looking at a wide range of chemical compounds. So one of the main metrics I used was to calculate the exposure in units of part per billion hours. And it's basically the area under the curve of the concentration versus time graph. So you can see I defined post-disinfection as the hour after the disinfection event, and pre-disinfection as the hour prior to the disinfection event, as more of as the baseline. So looking at our results for the bleach experiments, the y-axis, or the x-axis, is the chemical mass per charge. So you can imagine from the chemical reaction equation I showed in the previous slide, there's basically a hydrogen ion, or a hydrogen H plus attached to each molecule. And so the mass is the mass over that one single positive charge. So it's basically the chemical mass here. The y-axis is the log of the ratio between the post-disinfection and the pre-disinfection. So you can imagine anything above 0 would be enhanced by the event, and anything below 0 would be depleted. You can see that from the first look that many compounds are very much enhanced, and this is a log scale graph. So this is twofold, 10-fold, 100-fold increase, and so on. And you can see there's a lot of chlorine-containing compounds, like monochloramine and dichloramine, which is what I discussed earlier in the background, as well as much more trace compounds. This color scale is the abundance, and so the red and the yellows are much more abundant than the blues. Another thing to notice is that the scientific grade bleach for most compounds are much lower in enhancement, and so that would show evidence that they don't have as much of those VOCs inside. Looking at a few examples, looking at the chloramines that we talked about earlier and comparing to the home chem experiments, these chloramines are resulting of hypochlorous acid and ammonia concentrations. And you can see here that in the home chem experiments, they reached 60 parts per billion. We only reached a little bit below 10. And that's because the application methods were much different. They used mopping for many minutes, while we used surface spraying, so there was less mass emitted into the space. And there was also quite a big difference in the air exchange rate. So 0.6 per hour leads to very stagnant air. So these concentrations are elevated for longer periods of time. Looking at a few other compounds that are chlorine containing, as well as a few other hydrocarbons, you can see that the exposure ranges from a few ppt per hour all the way up to a few parts per billion, parts per trillion, and parts per billion per hour, or hours. Looking at the hydrogen peroxide experiments, this is from the iodide SIMS, which is iodide chemical ionization mass spectrometry, which basically just, instead of the H plus adduct, it's an iodide adduct. And we see that the hydrogen peroxide concentration gets up above the NIOSH permissible exposure limit, which is a signal of dangerous levels, very briefly, but only for a few minutes. But you can imagine what would happen in the Valley Metro rail public transit case, in that spraying this much hydrogen peroxide around in an indoor space would lead to a lot more higher elevations, and with a lower air exchange rate would lead to much elevated concentration for longer periods of time. And so the hydrogen peroxide concentrations in those spaces could reach quite dangerous levels. Looking at the hydrogen peroxide experiments from our Vocus mass spectrometer, kind of the similar style as the bleach, with the enhancement being above 0 and the depletion being below 0. And we see a lot of nitrogenated compounds, as well as some oxygenated compounds. I'll take a few examples. The first is in this range here, from about 150 mass units to 200. We see a lot of C6 and C8 compounds that are quite high in molecular weight, which shows that there's a lot of different compounds in the hydrogen peroxide. Another example is acetanilide and its byproducts of aniline and nitrosobenzene. Acetanilide is used as a common hydrogen peroxide stabilizer, and it was actually used in the previous century as a pain reliever before realizing that it could cause kidney and liver damage. And its toxic effects are pretty well characterized. And you can see here in the personal action criteria, a dangerous level, the lowest level is about 360 parts per billion. And we reach only about 10 or 12. And so those levels aren't dangerous in our experiments, but they could be in other scenarios. Finally, we'll look at some pilot results of the effectiveness of different masks. And so I defined the pre-mask concentration as the ambient chamber concentration and post-mask as what a person would actually breathe in. We used a breathing mannequin. We named him Steve. And every 2 minutes, we would switch between an inlet in the chamber air and the breath. And you can see here that this is kind of all the data. So you can see that every 2 minutes, we switched between the different lines. And you can see the monochloramine was a fairly effective, or the mask did a pretty good job of masking the monochloramine. Looking at both the hydrogen peroxide and bleach experiments, we see that fortunately, a lot of the compounds are filtered by the mask, which would be below 0, and especially the ones that are most concentrated, are most abundant, the monochloramine and dichloramine, as well as the acetanilide that we talked about earlier. But there also are a few compounds that are elevated, especially ones that are much higher mass, like that contain oxygen and nitrogens. And we speculate that there's a bit of reductions because the mask filters out the droplets that are still in the air before they have time to evaporate. So for some conclusions, both hydrogen peroxide and bleach contain a wide range of volatile organic compounds. Bleach results in a lot of chlorine-containing compounds, while hydrogen peroxide results in a lot of oxygenated and nitrogenated compounds. And our initial pilot studies show that masks do reduce the primary compounds, but show signs of larger molecular weight and secondary compounds that are enhanced. So some personal recommendations. So you might be scared by all the things that I've shown you about different concentrations of what look like pretty scary chemicals, but I would just recommend, if you're using these things at home, to ventilate and ventilate and ventilate and try to flush out concentrations as quick as possible, basically to get a very high air exchange rate. For the future work for the stage two, we're going to look at different kinds of masks and explore that a bit further. And then as far as how we could work for the sensor lab, we hope to work with you all to look how different low-cost VOC sensors can be valuable in many indoor spaces rather than just our instrument. So thank you so much for watching. Be sure to follow Sensor Research Group on Twitter at SensorRig. And if you have any questions, you can email me or my research advisor, Pavel Mishtal, at the emails listed below. So thank you so much, and I'd be happy to take any questions.
Okay, thank you very much for your amazing presentation. Now let's wait for the questions to come in. Okay, while we are waiting for the questions, I have a question about the effectiveness of the face masks. I just realized that wearing face masks can even enhance the concentration of certain compounds. So do you have an idea of what characteristic of those compounds have in common so that they will be enhanced through wearing face mask?
Good question. So there are a few different reasons why there could be enhancements in the face mask. The main reason would be the surface chemistry of the mask material and how that might interact with different compounds and droplets that kind of attach to the face mask. So the surgical face masks we used for our initial pilot studies are relatively porous compared to N95. They're not meant to filter out the smallest particles. And so there's interesting surface chemistry that will definitely be looking at more closely in our second stage. Okay. I can't give an actual chemical group or anything that would be most interesting, but yeah, surface chemistry is, in a nutshell, that's what's most important.
Yeah, that makes sense. Okay, I think there's a question coming in. Um, there's a question that will you be looking into the differences in DBPs produced by different application process? For example, laser wipes or similar materials versus aerosolizing disinfectants.
Yeah, thank you, Emma, for that question. So DPB would stand for disinfection byproduct. So the things that are resulting from our sprays. So interestingly, I didn't talk about it at all in this presentation, but we did headspace tests of many wide range of wipes and other not just bleach and hydrogen peroxide disinfection ingredients. So far, I don't think our plan is to, I think we're going to try to stick to the spraying method or the vaporizing method, because that's what the foggers I showed in schools and in the White House, that's what they do. But I think it'd still be very interesting to see what kind of wipes or other methods would result in different VOCs. So, yeah, thank you.
Okay. Okay, if you have any questions, you can type in the chat box or unmute yourself. Okay, there's another question coming in. Since the masks were very porous, does that mean pretty much all the airborne compounds penetrates through the mask?
Yeah, good question, Sarah. So one of the most interesting things that we'll try to look at is the differences between the surgical masks, which are relatively porous, versus the N95 masks and even very burly respirators, to see how that might change the reduction in exposure. So what we think is expected for the filtering that we see from the surgical mask is that there's droplets that don't get a chance to evaporate and breathe in. They're blocked by the mask. But yeah, I think there could still be gaseous compounds that are breathed in through the mask, because the mask would not filter the gaseous molecules. So,
yeah, okay. Okay, there's a question from our live YouTube channel. Did you look at face mask changes with no disinfectant yet?
I think, I'm not exactly sure. I think we did do some initial background tests, of baseline tests of the mask without any disinfection, because that's definitely a thing we need to do for quality control. If we see a spike in the mask without any disinfectant, then we can conclude that compound is due to the mask material and not different surface chemistry with the disinfectants. And so we will subtract that for the stage 2. We'll be looking at that much more closely and subtracting that from anything that we see from the disinfection events.
Yeah, okay. Due to the time constraint, we'll take one last question. Are there safe exposure limits in ppm or ppb, indicating that it's dangerous to exceed those levels even for an instant in time, or are they for a certain duration of exposure?
So yeah, thank you, Emily, for that question. I will have to do a bit more research on the exposure, what metrics are being used. I believe for the concentrations that I listed, those were for much more acute exposures and not exposures that people would be under for longer periods of time. What'll be interesting to see, because in movie theaters and in schools, these foggers are disinfecting, and then if they expect people to be in the movie theater for another 2 hours, of the school for the rest of the day, that would be a lot more exposure than a cleaning worker spraying and then leaving the school. And so it'll be interesting both to see, I didn't include this presentation, but I've also calculated not just the first hour after the disinfection event, but maybe the area under the 2nd to 4th hour, or the 5th to 10th hour, and looking at different exposure as it decays. So that'll be interesting to look at for the future. A good question, though.
Okay, if your question is not answered or you have further questions, please email to Daniel at the email address provided here. All right. I'd like to thank you again for your great presentation, and I wish you all the best in your future work. I'd like to thank our audience as well for joining us today. Our next talk is, please give me a minute to share my screen. Our next talk is fluorescent probe design for active metal enzyme sensing, given by Dr. Radhika Mehta on October 23rd. We're very much looking forward to see you in 2 weeks. Bye.
Thank you all for inviting me. This